Good morning, everyone. We are pleased to welcome Dr. Jude Onwudili today, a very special keynote speaker from Birmingham, UK here this morning. Dr. Jude is a senior lecturer and a chemical engineer. He has research expertise in the advanced thermochemical processing of biomass and bio-oils for production of fuels and chemicals, over 110 journals, papers, and 2 book chapters published, with over 4,400 citations and a H-index of 38. He leads a research team in his group at Energy and Bioproducts Research Institute at Aston University. Dr. Onwudili is EBRI Deputy Director of Industrial Engagement, leading the efforts to link academic research with the needs of industry. In addition, he is engaged in international collaborations with researchers in Brazil, Nigeria, Colombia, India, Kenya, South Africa, and several European countries. Dr. Onwudili is also a consummate higher education teacher, a senior fellow of UK Higher Education Academy, and a fellow of Royal Society of Chemistry. Today, Dr. Onwudili will share his expertise in this Keynote 2 session entitled Hydrothermal Processing of Biomass and Wastes for Fuels and Chemicals Production and Materials Recovery. I would like to thank you for being here with us, and I'm very gratefully and to present you my colleague and postdoc supervisor, Dr. Jude Onwudili, and would ask a warm welcome and your full attention to him. Thank you.
Thank you very much, Dr. Karini, and I'm very, very grateful to be here today to talk to you about the research we do in my lab in Aston in EBRI. So thank you so much for the invitation. It already feels like home coming to Brazil, so thank you. Right, so today I'm going to give you some overview about the research we do in my group, and starting from my PhD, where my topic was on hydrothermal processing. One of the first people at the University of Leeds to work on this project, this title, and we have continued to develop it. So like Karini mentioned, I work at Aston University. So thank you for having me. So for this presentation, I'm going to go through some general introductions to Aston and to my research institute, which is one of the flagship institutes in Aston. What that means is one of the main institutes that we carry out research in Aston. And then I'll introduce hydrothermal processing and talk about the work we've done with plastics, with biomass. Of course, I'm not going to be able to tell you everything we do, but some of the highlights, the key highlights of the work we've been doing. And then I'll conclude at some point, hopefully in good time for questions. My university, Aston, it's right in the middle of Birmingham. It's not a new university. It used to be a polytechnic, as you see, but it has a very unique community of people, students, and staff. So it was founded in 1895, and it was UK's first college of advanced technology, and of course became a university in 1956. So like I said, it's at the center of Birmingham. It's relatively small, which means you get to know so many people so quickly once you join. So it's a closely knit learning and research community with over 1,200 employees, 11,000 students. The bulk of our students are undergraduates, as you can see. And we have 5, well, we'll call them colleges now. So I work in the Engineering and Applied Sciences College, and we have other colleges like the Life and Health Sciences, Languages, the Medical School, and the Business School. And so we have a lot of international students. So you can see where we are located at the center of Birmingham. Now, just a brief overview of my research institute. We call it EBRI. So we see energy as being essential to life, every form of life, microscopic, macroscopic life. And we know most of our energy, if not all, comes from the sun. And therefore, we try to see how we can use energy as a driving force for future development. And we know human development has only occurred because of the way we have transformed energy and the use of energy. So EBRI stands on its own, so it gives us the flexibility to work, within our own rules, of course, linked directly to some departments in the main university. And we have 21 academics and associates linked to EBRI. We have 12 research fellows, including one of your friends here, Karini, a number of admin students, and currently we have 24 PhD students. So our main focus is in fundamental research, developing technologies, working on large projects, and looking at industry collaborations. And like Karini mentioned, my role as a deputy director in EBRI is to look at how we engage with industry. And it's just been 2 years, and we've done quite a lot, and I can already see the range of collaborations we can have with Siintec. So we do fundamental research, but our main areas are focused on characterization of biomass and different feedstocks, reaction products, and then we look at the conversion processes where my expertise is. So converting biomass and waste into valuable products. And we also have the evaluation of our processes, as you all know, in academia, to be able to transform our research into industrial scale. We need to show that it can make people money. It can be developed at a large scale. So we have the people in our team who work on techno-economic analysis, life cycle analysis. And now we're beginning to see that we can only develop processes to industrial scale if we integrate different technologies, not just the thermochemical, even with the biological and catalysis. We have a wide range of analytical equipment for different phases of the products and feedstock we deal with. So we have a research strategy group in EBRI, and it is led by our director, Professor Patricia Thornley, and Professor Bridgewater. I know most of you may have read about him. And I work with my colleague Paula in dealing with the thermochemical conversion. So we all work together to make sure EBRI is relevant to Aston and relevant to industry. So in terms of our facilities, because we started EBRI based on thermochemical processing, we have very wide range of capabilities when it comes to thermal processing. So we have small scale, batch reactors. We have some medium scale. We have pilot scale plants right around our building. So we can go from 1 gram per hour to 50 kilograms per hour. So we have all these capabilities with fast pyrolysis, with intermediate pyrolysis. We also have gasification capabilities from 10 kilograms per hour to 400 kilograms per hour. So that's almost industrial scale. So you can see some of our facilities at the back of our main building. And from the gasifier that we have, we can feed the syngas into a 400 kilowatt CHP engine, which is located at the base of the building, at the base of the plant. And right now, we're also using it to help in developing models, in helping industry to understand the basics for not just the chemistry, the chemical engineering, as well as the scale-up. So there we are in terms of our development to produce power and heat. Our capabilities, I already spoke with some people here about analytical chemistry and analysis. So yes, we also have such capabilities, and we can already see some links that we can do. So all the range that we cover, from the feedstock to the different products, we are able to characterize and work with industry to give them some data that they can use for scale up. So I mentioned before, we have techno-economic feasibility and sustainability experts. So we do from little research to demonstration to process modeling. We're very interested in carbon capture as carbon accounting as one of the ways to actually hit the net zero that everybody is talking about. So we're in the middle of, working towards sustainability and net zero. There are many demonstration plants that we are involved in terms of the scale-up that I mentioned. So we have a website that you can visit to see some of the work we've been doing. We also do a lot of training of our students. So again, just like Siintec, you have these big facilities to show your students. We have these facilities to train our undergraduate and postgraduate students. We recently have a continuous professional development course accredited or approved by the ICME. So we can bring people from industry and give them master classes and teach them and train them, on how to use some of the technologies that we have developed. Right. So I'm going to go into the technical aspects of what we do in my research group. So, of course, some of you may know, but we work with hot pressurized water media, which we call hydrothermal media. So what is this? Why is it relevant? All the types of work we do in terms of biomass processing and waste processing are based on those three technologies: pyrolysis, gasification, hydrothermal processing, which is what I'm actually leading in EBRI. And I have colleagues who work on these areas, and they're all underpinned with some kind of catalysis. So we have a very strong catalysis team in my research institute. So we see these thermochemical technologies as a way of transforming organic waste into solids, liquids, and mixtures of gases. Of course, if you deal with this kind of processing, you can tell that we are able to tune the proportions of these different products as we like. So if we want to make biochar, for example, we change the technology, tune it to make more solids. If we want liquids, then we can do the liquefaction or fast pyrolysis. If we want gases, we go for gasification or high temperature pyrolysis. And we feel that the impacts of these kind of products and this transformation will be for resource efficiency and drive sustainability, because we're dealing with recycling in most cases and reapplication of waste materials. So what then is the hydrothermal media? So we understand it using the phase diagram of water. So this is the triple point, and then we have solid, we have liquid, we have vapor, water as vapor, and then above the critical point of water, which is 374 degrees Celsius, 22.1 megapascals, you have one single fluid phase. It is no longer liquid nor vapor, so it makes chemistry very, very interesting in this region. But of course, it requires very high pressures, which may be a problem for industrial development. But what this shows us is that we can operate within the different phases of water and carry out some chemistries. For subcritical water processes, we can make use of the very high ionic products of water. We all know the decomposition or dissociation of water is endothermic. So as you heat it up under pressure, it produces more hydrogen and hydroxide ions, which can be used to drive some reactions that require hydrolysis, for example. So the water can act as a catalyst, it can act as a medium, it can also act as a reactant. And then we have the subcritical water processes, which is now beyond the critical point of water. And here, one of the things you see here is the very low dielectric constant of water. It means that water is able to solubilize organic molecules than it would have done under ambient conditions. So many organic chemical reactions can be carried out. And so the key features are that we can have very fast reaction rates, very high mass transfer, very favorable thermodynamics. We are looking at temperatures between 200 and 500. Excellent heat transfer because there's plenty of water in the system. So water helps to control the temperature. And there are so many different chemistries that can be exploited in this media. And so I have put together here some classifications based on my experience. People may disagree, but if you look at the different phases, you can see that in this region, we can carry out a lot of carbonization, then liquefaction, and then gasification. So as the process intensity increases, then you can change the chemistry from carbonization to liquefaction and then gasification. And so we can have two main broad areas, subcritical and supercritical, and we can carry out all these kind of reactions. So the work that Karini is working on is on aqueous phase reforming of glycerol, and we have worked on depolymerization, and you can see some of that depolymerization today. And of course, the gasification, which supercritical water oxidation and gasification, which were the bedrock of my PhD thesis, which is what we still carry out. And you can see the different products that you can get from carbon, in this case, hydrochar or biochar, if it is from biomass. You can oxidize and produce hot water, which can be used for electricity. You can, of course, recover monomers, recover some solid materials. So you see some of this in some of the slides I'll show. We're looking at making fuel gases, so hydrogen, propane, methane, and then we can produce some oils as well. So the first area I would like to talk to you about is the processing of plastics. Now, of course, we know what the problems with plastics are. there are so many different types of plastics. And it is not because we like to make plastics, and that's why we keep making new ones, but just because they have very special properties. So different plastics have different properties, and therefore we keep making new ones and using them. So you can see cumulative production since the 1950s has gone up to 8.5 billion tons. And so what do we do with these plastics when they reach their end of life? So this is 1 week's plastic production from waste plastic production from my house. Okay, so I took a picture of this just under 1 week, from my own house. And I think that's the same for most people here. We make plastics because we need it for food packaging. Some can stop a bullet because they are very thick and they have very good mechanical properties. Some can provide cushion when we fall. Sports people use a lot of plastics. They can make vehicles lighter, lower the fuel consumption of vehicles. We use them for clothing, most of our clothing, polyester, polyamides, and we use them for insulation in electricals. So they are very good in terms of the properties they have, and the variability of their use is also very well known. But when we reach the end of life, what do we do with them? Now you can see from my bin here, there are different types of plastics. Some are light, some are very thick, some are polyethylene, some are polypropylene. So what do we do with them? Normally we throw them away. So they become, we say they are a wonder to use, but they become nightmares when we throw them in the refuse. So what do we do with them? Now, some people propose mass conversion, maybe using pyrolysis, but we know there are issues because some plastics are quite difficult to process. So these are some of the challenges when plastics reach their end of life. They are everywhere. They are persistent. They don't degrade. We don't like the sight of them. Some contain very harmful chemicals that can leach into the environment. Some, of course, most plastics are combustible, which means they can ignite in waste dumps, causing fires and air pollution. There are so many single-use plastics around. Of course, there is also the problem of microplastics in the oceans. So there are so many issues surrounding plastics. So what do we do? What are the potential solutions? Probably let us ban the use of plastics. That's potentially not looking likely. Can we reduce the use? Can we reuse them? Potentially, yes. Can we recycle them? Yes. There's a lot of recycling going on, but maybe 20%, 30%. Can we use chemical recycling? Yes, pyrolysis and all of that can do that, and hydrothermal processing. Energy recovery, can we just burn them in incinerators and recover the energy? So yes, we can do that. But because of some of the components present in plastics, this is problematic. We need to sort the plastics into different fractions before we can use them. So the methods for chemical recycling are given there, and we'll talk about the hydrothermal processing in a while. Now we need to focus on some chemistries when it comes to hydrothermal processing. I showed one of the slides where we have the different processes that can occur under hydrothermal conditions. So we can classify the use of hydrothermal processing based on specific chemistries. For example, based on applicable, I will call this initial chemistries for specific plastic types. For example, we can look at hydrolysis and depolymerization of some plastics like polyesters. It still requires sorting. We can look at dehalogenation of PVCs and other halogenated plastics like Viii plastics from waste electrical and electronic equipment. We can look at random chemistries, which of course doesn't look specifically at maybe hydrolysis, but in this case, we're looking at free radical or free kind of reactions, some cascade chemistries. So liquefaction, supercritical water gasification. And we can have some combinations of these as well. So those are the kind of chemistries we can carry out. And so we look at the halogenated plastics like PVCs, brominated plastics used in electronics. And you can see the composition of these different plastics in the equipment we use. This is personal computers. This is mobile phones. So you can see different types of plastics present. In addition, you have other components like metals. So this is as heterogeneous as it gets, you know, because you have all sorts of plastics and metals combined in this kind of materials. So what are the kinds of plastics used? The main ones are brominated acrylonitrile butane styrene plastics or brominated high-impact polystyrene plastics. So they take the bulk of the plastics in waste electrical and electronic equipment. And these are the monomers. Can we recover these monomers from the waste? And then they are used in addition with these flame retardants because you want to stop your electronic equipment from catching fire when you use them. So we use these flame retardants. This has been banned since 2006 in the EU, but we still use this tetrabromobisphenol A and hexabromo cyclodecane is still being used. And you also have antimony trioxide used as part of this process of stopping fire. So that makes life a little bit complicated. So we're going to look at the PCB, the printed circuit boards in plastics. It contains up to 15 weight% of these plastics. And there are up to 50 million tons of these PCBs generated. We all know how often we throw away our mobile phones and get a new one. So we are contributing to the tonnage of waste electrical equipment and therefore PCBs. There are ceramics, there are metals present. And so you can see how the motherboard, we call it, looks like. And you can see its composition here. Therefore, we have the potential to recover some materials from these waste plastics. For example, the recovery of bromine. We know bromine is mostly produced from the Mediterranean Sea or around there by Israel. I think more than half of the bromine, if not all, is produced around there. And so about 500,000 tons of bromine is produced and used every year. And therefore, if we can recover it from waste plastics, that will help in sustainability. And so you can see where we are. In the EU alone, about 12 million tons of Viii plastics, and that can contain up to over 300,000 tons of bromine. So we expect that using some technologies to recover bromine from Viii plastics can be very helpful. So in our experiments with some batch reactors that we have in our lab, we have this feedstock. Of course, most of these plastics come dry, but we need water for the reaction. So this is the scheme of the reaction. And we, at the end, analyze our products. So we can use homogeneous catalysts, we can use heterogeneous catalysts, and then we have our analysis. So for our brominated plastics, so model brominated plastics, this is the kind of experimental process we carry out. So we can carry this out in 2 stages, where in the first stage we carry out dehalogenation, so debromination of this, and then we have the hydrocarbon backbone, which we can now further process in order to get oil, gas, some solid, and of course aqueous phase from the water. And we can carry out some supercritical water processing in order to end up here with some hydrocarbons. Of course, depending on the catalyst we use, we may end up having some carbonates formed. So this is the work we've done with BR HIPS, high impact polystyrene. And so, of course, that's the TGA and DTG profiles of this plastic. And these are experimental conditions. You'll see soon why we have used sodium hydroxide in this case as a homogeneous catalyst, apparently because of the high bromine content, and therefore we end up with a lot of acidity in the system. And we have all sorts of analytical techniques used to look at the gas product, the liquid products. You can see the liquid products, being less dense than water. So there's water at the bottom, and then we have our liquid product. And the solid product, we carry out a range of analytical techniques to measure the carbon, hydrogen, and nitrogen contents where possible. So this is some of our results, different conditions, just to point at some of them. So you can see that without alkali additives, the pH of the liquid we get is around 1, so very acidic. We were only able to run this experiment once because at the end of the experiment, you could see that the reactor was suffering. So we didn't want to continue to damage the reactor, but you can see here a pH of 1. But by adding the alkali, you see our pH at least goes up to above 7 in some cases. And we got very little char from this and a lot of oil. So we're able to produce a lot of oil. So as you can see from there. So almost all the antimony ended up in the solid phase, and all the bromine, nearly 100% bromine in the liquid phase. So we can recover the bromine from the aqueous phase. And you can see, again, the distribution of our bromine and antimony under different conditions. So we're particular about how we can get bromine out, recover bromine, and produce an oil-free bromine, because that's one of the issues with thermochemical processing. The bromine reacts and form compounds in the oil. So this is the bromine content of the oils, as you can see. Depending on whether we use enough sodium hydroxide, we have, these are bromine compounds, which we couldn't quantify, by the way, because there were so many, and we were using the electron capture detector. So, but it was able to show us, how we go from this without any sodium hydroxide to this with some sodium hydroxide. And when we have optimized it with the sodium hydroxide, we are able to get fewer bromine components in the oil. And the oils are similar to what you get from pyrolysis, apart from the brominated compounds. So a lot of or aromatic hydrocarbons, because Of course, they are all based on styrene monomer, so you expect all sorts of aromatic compounds which can be used for as chemical feedstock. And then we looked at heaps, the same kind of processing, but this time we had to grind it, to sieve it, and then process it the same way. And these are the properties, the physical and chemical properties that we looked at. And again, see here, of course, heaps, the printed circuit board being mostly solid materials. You see some ceramics, some metals present. So majority of the product is solid residue, and we got a lot of gas out of this and some liquid. So, but most of it was solid residue, which of course you can't convert using thermochemical processing. And here you have the degree of depolymerization of the epoxy resins and different plastics in the waste printed circuit board. And here you have the gas products and yeah. So you have a lot of gas products, mostly CO2 as the gas due to the chemical reactions occurring. And these are the results in terms of phenol recovery, because the epoxy resins are made from phenols, and the also you have the tetrabromo bisphenol A present. So we could recover 48% of the phenol based on the PCB itself, and 63% based on the resin itself. So that's a GCMS that shows us the recovery of phenol. It was actually both phenol and aniline that we eventually found from here. And this is the solid residue, which is mostly metallic in nature, and of course with some ceramics. And this is one of the things we're working on now, how to recover the metals. So we're using a lot of chlorination chemistry in order to get some of the metals out into solution. So is it being used in industry? Yes, there are some potential large-scale application of hydrothermal processing for plastics. You can see some plastic is catalytic hydrothermal recycling, they call it here. It's being built in the UK, so it's being funded by the UK government for the conversion of plastics or different types of plastics. And so there is possibility of using this if you can have it on a badge or have it on a ship. The technology, it can be used to get rid of waste plastics in the oceans. So this is a potential application. Now for biomass, which is what Brazil is known for, because that's why we want to come here, you will quickly see from this graph that this is what we think that can be exploited. The world's energy production or consumption is around 600 exajoules per year. And this is a study that I got from a slide I got from my director, Patricia Thornley, which shows that if we are doing this business as usual, then these are the contributions with biomass, these different biomass resources. We call sustainable biomass resources, agricultural and forestry residues, industrial and municipal solid waste, wood, energy crops. So you can see gradually up to 2050, depending on whether we are doing business as usual or we are using moderate policies or very strict policies, we can contribute up to 140 exajoules per year from the world's sustainable biomass. And Brazil has a very big role to play in this. For the UK, maybe that's why we want to come to Brazil, because you can see most of our biomass and waste are from, very small fractions here and there. So in terms of bioenergy, UK will not be self-sufficient. And as you already know, we have a bioenergy power plant that produces about 7% of UK electricity from biomass. But where does the biomass come from? The US and Canada. So they ship it all the way from US and Canada. Of course, there's still some benefits in using it, but the collaboration between us, between the UK and South America and Africa, because this is where the biomass is. So it's very, very important in order to drive the contribution of biomass, bioenergy to net zero. So what are the relevance of HTP of biomass? In the UK scenario, a lot of the technologies are based on pyrolysis and gasification. But majority of the waste resources in the UK are wet wastes. For example, sewage sludge, anaerobic digestate, crude glycerol from biodiesel production. There are a lot of industrial organic wastewaters. So yes, you can use AD, but you still have some leftover digestate from AD. So in terms of UK, it looks like in order for us to use the majority of our biomass resources to expand the resources we have, we will need to first dry some of this, which is energy intensive. And therefore, we think there is a role for HTP because it uses water as a reactant, it uses water as a reaction media, so it can help to increase the availability of biomass, especially for UK. Maybe not for Brazil, but of course, certainly in the UK, we need to be able to exploit these various chemistries to process these waste materials that we have to increase our bioenergy penetration. So one of the current projects we're working on is funded by the UK department, UK government, and we call it the Harrow Project. And it's between Aston University, of course, EBRI being where I do my research, and a company known as EBRI, and it's a process engineering company. And so it came from the work we've done with this little reactor you see here, just octoclave, that showed that we can process bio-oil into cleaner, liquid, but produce a lot of fuel gases. So we have demonstrated that we can carry out aqueous phase reforming, and therefore we can produce gases like methane and hydrogen from this aqueous phase reforming, depending on the catalyst we use. And of course, we know that there are technologies that exist that can transform methane to hydrogen, because you all know maybe tomorrow's panel will be discussing more about hydrogen as the future fuel. So we can already carry out steam reforming of methane. The technology is well known. And of course, the water gas shift reaction to produce more hydrogen is very well known. So we are looking here to demonstrate this at a continuous scale, and that's the whole objective of this project. And so we found a supplier, Oleco, who supplies crude glycerol and digestate, and of course we have EBRI that can look at the engineering. Okay, so EBRI, I'll just talk a little bit about them because it was quite stunning to find that there are, companies that are willing to take risks, to try things. They are not a research institute, so it was quite interesting to see that they wanted to work with us. So they have their capability in terms of trying to scale up small processes like the ones we have. Okay, so this is the concept. And so we have feedstock, whatever it is, maybe crude glycerol, digestate, or sewage sludge. And we can make it in such a way that it is pumpable. Maybe some pre-treatment will be required to make that happen. And then we pass this through a catalyst bed, which we call the aqueous phase reactor, where methane is produced. So it produces methane and some carbon dioxide. Not a lot of carbon dioxide, but mostly methane. And then the methane is, the product is depressurized, and we go into the methane reforming reactor here, and then we can carry out the water gas shift. But one of the reasons we got the grant from the government is our proposal to capture the CO2. Because you all know there's no way you can produce hydrogen from biomass without producing CO2. And so that is a big drawback for biohydrogen. But now, if we can capture it, we're not only making it neutral, we're actually going to negative emissions. And that is where bioenergy capture and storage is contributing to net zero. So we're going towards negative emissions, so we can balance things up by 2050. So that is one of the reasons we got the funding, and that's what we've been looking at. So this is the chemistry we think is happening. Some of this has been published, so it's fine for us to show you. But we're looking at this first stage here, where we get lots of methane produced. So rather than wait for the AD to produce biogas after so many days, we can, in an hour, convert any liquid organics to methane and CO2. So we were thinking we'll get some ratio similar to that of biogas, but we're actually getting a lot more methane than we expected. So, and then we can reform the methane and produce the hydrogen. So, of course, being a batch reactor, we haven't been able to do a lot of the reaction kinetics. So that's what we're looking at now. And the laboratory rig has been built at ICMIA, and we've been to see it, and we were all very delighted to see the progress they've made. So this is one of our first results. As you can see, just showing you the chromatograms from the gas analysis. So we actually analyzed the gas at Aston. And what's interesting is that we are able to show that we can convert crude glycerol to methane. Now, I said before, our reaction stoichiometry showed that we were going to make CO2. But we found instead that we were making more carbon monoxide, which of course makes sense now, because using a batch reactor, we had so much residence time that majority of this carbon monoxide got converted to carbon monoxide got converted to carbon dioxide and hydrogen. So we are not seeing a lot of hydrogen, but based on the mole ratio of carbon monoxide to hydrogen in the water gas shift, we now see why we got a lot of hydrogen and a lot of CO2 in the batch reactor. So this is the progress we are making, and both the company and myself and my team, we are very, very delighted with this. So this is the demonstrator concept that we're planning, because the funding is in 2 phases. So this is the first feasibility studies, and then we are going for a demonstration plant next year. I think that's about £5 million project. So we haven't applied yet, but we have some kind of hope that we can do that. And with your collaboration, I think we can actually bring you into some of this to see where we can develop this further. And we have also done some work on biopropane from biomass-derived feedstocks. So we've used butyric acid, and this work is being funded by an industrial partner. So I think you know them here as super gas brass. Yes, so they are called SHV energy or color gas. So they came to us looking for solution to make biopropane, bio-LPG, and we were able to show them that we can make propane by just decomposing butyric acid in the presence of a catalyst. So this is just a snapshot. The project is now going further with a PhD student being recruited to look into this in more detail. All right, so coming to the end of the presentation. So we think hydro processing can help us to enhance renewable energy production from biomass and ways that cannot typically be used for pyrolysis or gasification, as the case may be. It can expand the availability of biomass and waste feedstock for bioenergy. We can carry out different hot pressurized water-based chemistries, and it can be a solution to different difficult to treat waste materials like plastics. It can help us to deal with the plastics in the ocean if we have the courage to do so, and it can save a lot of energy from the drying of wet feedstocks. Liquefaction that we've been carrying out, we can produce a lot of liquid biofuels or liquid fuels from plastics. We can recover monomers. We can carry out reforming to produce renewable fuel gases. Like Karini is working with us on. And we're developing new catalysts to help us enhance the selectivity towards the different fuel gases of interest. There's still work to be done in terms of the techno-economics and life cycle analysis. And the project that the government is funding, the project I showed you, will enable us to carry out those studies on the production of biohydrogen, which can be replicated on other fuel gases. So thank you very much for listening, and I need to thank my sponsors, the funders who provide the funds to do the research, and of course my team, Karini being one of the leading members of the team. It's a shame that she has to come back at some point, but we really, really like her, and she's been doing fantastic work for us. So thank you for your time today, and I'm happy to take questions. Thank you.
Thank you, Dr. Jude, for sharing with us this brilliant presentation. Thank you very much. We really appreciated it. So we will open for many questions. We have time for 2. If somebody here wants to make it.
Hi, good morning. First of all, I'm a physician, so excuse me if my question is too simple for you, okay? I'd like to know, you mentioned that waste that's difficult to treat. Since I'm working in a hospital, how this type of process can be used for hospital wasting, especially if you have a contaminated material? And what's the size of this hydrothermic power plant?
Okay.
Thank you.
All right. Thank you very much for your question. I also happen to teach 2 modules in renewable energy in my university. And one of the topics I teach is autoclaving. So in the UK, and I think in the US, they've developed this hydrothermal processing, but they call it autoclaving. And they use a very big drum, up to 1,000 liters, and they use it to treat hospital waste. So what they do is it performs 2 roles. Hospital waste can contain human waste, can contain microorganisms, pathogens, can contain plastics. So what they do is they use this to sterilize, and at the same time, to convert all the plastics into fiber. And that fiber can be processed using pyrolysis to make oil and all of that. So it requires this pre-treatment of this hospital waste. So there are companies in the UK, even in Birmingham, using this type of technology to process medical waste. I said about 1,000 liters is the size of the reactor. Thanks.
One more question? Any questions online? So we want to thank you, Dr. Jude, for being here with us today. Thank you very much.
Thank you. Thank you for having me. Thank you.